Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about angular speed and angular acceleration. We said angular speed it is the time rate of change of angular displacement and it was measured in radian per second. As for angular acceleration we said it is the time rate of change of angular speed and it was measured in radian per second squared. We also talked about their equations and how we can use them in calculations. And then today, that is a new section here. We'll begin with section 1.2, and that is going to be the relation between linear quantities and their angular quantities as well. Because up to this point, we were only been talking about let's say, the angular quantities here. But from now on, we're going to talk about the relation between the linear and their angular quantities. And the first thing to start off with, we have an example. It says, imagine a golfer wants to hit a golf ball. The most effective method to hit the golf ball along a large distance, let's say, is to swing the golf club at approximate circle around the body. Okay, what is the purpose or the benefit of this? Because once you're swinging the golf club at a large circle, of course now the golf club, or you can say the club head, is going to undergo a large angular acceleration. That large angular acceleration leads to a large linear acceleration. And of course we can say this large linear acceleration of the club head, it is going to strike the ball at a very high speed and producing a significant force on the ball, which makes it travel very far. You've seen that on TV perhaps. If they wanted to send it far, they'll make the swinging, or they'll swing, like their body the most, and then they'll make the circle very, let's say, the largest. But if they want the golf ball not to travel that far, then they'll just hit it at a small circle. They'll just hit it at a small, you can say, angular or a small angular acceleration so that it doesn't go that far. So that is clearly the link, the relation between angular and let's say their linear quantities. Once again, we said if the club head goes, let's say, or undergoes a large angular acceleration, that leads to a large tangential or linear acceleration. That is clearly the link between the two. But let's dive into the details and see how it works exactly. So the first thing that we have is tangential speed of a circular motion here. So what exactly happens, or what is tangential speed? Let's explain this one a little bit. Consider that we have an object or a circle. An object is moving in a circle. At one of the points, let's say this is, let's just consider this is the, let's say, the golf ball here. So once this golf ball is struck, let's say, then it's no longer moving in, let's say, or moves in a straight line. At this point, it is just going to go, let's say, it's going to move in a straight line. No longer it is, let's say, it does not move in a circle, just like the club head, let's say, or the golf club here. So this moving in a straight line here, that is what is called tangential speed here. Remember, we call it what? We call it tangential speed. Okay, so what is tangential speed at this point? We have an equation for that as well. The equation for tangential speed, it is equal to, we can say tangential speed, of course we're going to use V sub t for tangential, it is equal to angular times the radius. We know that this one, of course, has a certain radius here, so that is the radius. When this club, let's say golf club, is moving at a circle, certainly it has a certain angular speed as well. So angular speed multiplied by the radius, that would be the tangential speed. We know that tangential speed, just like this, the speed you've studied in last year, it is measured in meter per second. And can we, for example, what about this side here? For this side, of course, we know that angular speed, it is measured in radian per second. Let's just write it this way, radian per second. All right, and of course, this radius, it is measured in meter. But remember this, at any point, if you're going to combine radian with any other units, because radian is dimensionless, so it just gets, we could just remove from the equation here. So we can bring this meter here. So this side also becomes meter per second. And of course, we can say these two sides are equivalent here. So just remember the unit for tangential speed, it is meter per second. And what is the reason? Why do we call it tangential speed? Because it is tangent to the circle here. And what is tangent exactly? It is a line that touches the circle, you can say, at only one point here. What if it, let's say the object strikes the golf club strikes the ball at other points, for example, then of course that would have a different direction here. So now, how do we define tangential speed? Remember, the definition is very important. We'll say it is the instantaneous linear speed. What do we mean by instantaneous? That means the speed at that instant, the speed at that moment here, because from one moment to another, it could be different, and I'll tell you why different in a second. But let's get back to the definition. It is the instantaneous linear speed that is directed along the tangent of, let's say, the circular path, and it is measured in it's measured in meter per second. Why do we call it instantaneous? Because consider if the golf club, or it could be any object, for example, if it is starting to move in a straight line at this point here, then you can see that the direction would be different. What about if it was this point here? It would be different. What if it was this point here? So you can see that at every instant there will be different directions. This is why we call it instantaneous, because it could be different from one point to another. Now, if we dive into the details exactly, like where do we get this one here? Now, we know that when an object is moving in a circle, let's say going from one point to another, at any other points, let's say, it is clearly traveling at angle theta here. This, let's say, object, if it is moving in a circle, it is covering an arc length here. So, but what happens, let's just say, what happens if we make the time shorter at this point here? If we make the time shorter here, so, or you can say the arc length, that is the arc length first place, right? So, and that is a certain angle here, this is the arc length. But what if we make the arc length, let's say, smaller by using, let's say, a shorter time here? Then we know that the arc length would get, or let's say the angle theta would get even smaller and smaller. Let's say it was at this point first time, and this is the arc length that we have. But if we use a smaller angle, you can see that the arc length would be even smaller. And if we do that here, the arc length is going to be even smaller than the first time. So you can see that at this point here, the arc length is going to be very small. That is going to be almost like in a straight line here. So this arc length would be the same as, you can say, the delta x. And then, of course, if you divide this one by the time, like how long does it take to go from this point to another, then that is, of course, it will be the same as tangential speed in here. So now let's get back to this one. Where does this equation come from? Like the proving of this, it is not important, like it is not required from you, but of course, knowing this one, it is good enough. Okay, so in this case, if you just cross multiply the two here, we can say arc length that is equal to delta theta times the radius. But we said if the arc length is very small, I'll just erase some of those maybe. If the arc length is very small, then in this case, of course, this arc length would be the same as if, for example, it is moving in a straight line at this point here. So that small arc length in here, right, divided, like if we divide both by delta t here, then this one, of course, we said it's going to be the same as delta x. So arc length divided by the time, that would be tangential. And then we have here delta theta divided by delta time, that is going to be angular. And this is going to be times the radius here. This is where this equation, for example, come from, or becomes this one right here. So once again, tangential speed, it is the instantaneous linear speed that is directed along the tangent of a circular path measured in meter per second. And that's it, because it is linear speed at this point now. This is for linear speed, remember this. But what does the tangential speed depends on? We can see that it depends on both the angular speed and the radius. Don't forget this, and I'll have to tell you this at this point here. Let me just erase this one more time. So we said tangential, it is equal to angular times the radius. That means, watch this one here. Previously, we said when objects move in a circle, especially if it is, let's say, a solid object, all the points on the object will always have the same angular quantities. Do you remember? So when an object moves in a circle, all the points on the object could be point A, let's say, could be point B, could be point C. All of them, let's say, have the same angular quantities. These are not good circles. But we said they all have the same, let's say, delta theta. They all, like the points here, you can say for point A and point B here, they will all have the same angular speed, and they will all have the same angular acceleration. These are for both point A, and we can say for point B as well. That is for point B, and then angular for point B again, and then angular acceleration for point B as well. All these were the same. But can we say the same thing for translational? No, because you can see that clearly it depends on the radius here. So if I take 2 points here, let's just use this one maybe. Okay, let's erase this first, and we'll bring or use another circle. Imagine we have 2 points here in a circle now, this point here. So clearly that is one of, let's say this is the center. So we have point, let's say A at this point, clearly it has a certain radius, and we have point B at this point as well. Okay, so now does point A and B have the same radius? Clearly not. Which one has a bigger radius or have a bigger radius? That is going to be point B here. So remember, even if this is a solid or a rigid object, all these points have the same angular speed here. So we can say omega for angular speed for point A, it is the same for point B as well. But if we want to find their translational speed, would it be the same? The answer is not, because the radius of point B is bigger, so clearly it is going to have a larger tangential acceleration. Why is that? Because tangential, it is equal to angular times the radius. And now for, let's say, point A, it has a certain radius. Okay, these are the same for angular, is the same for both point A and B, but the radius for A, it is smaller than the radius for point B. Okay, so in this case, of course, times the radius for point B here. So even though these two are the same, but because point B has a larger radius, so now we can say the tangential speed for point B, it is going to be larger. And that is the first thing that we have, which is the relation between, let's say, angular, this is clearly the translational, the linear, and this is the angular quantity. So we can see that this is the relation between linear and angular quantity. That is for angular speed, don't forget. Translational speed, let's say. What about for tangential, let's say, acceleration? Of course, we have the same thing here. Imagine this time we have an object that is moving in a circle here. So at this point, let's say that is one of the points that we have, okay? And then this object, if the object it is going to accelerate here, let's say, and then this point decides to, here it could be the golf ball too. If it is going to move in a straight line at this point here, then we will have a tangential acceleration. Remember, in order to have tangential acceleration, you must have angular acceleration first, okay? So that we can have this two here. So this one, it is equal to, just like before, their angular quantity times the radius here. So we can say tangential acceleration, it is equal to angular acceleration times the radius. Just like, just like for tangential speed, it is equal to, let me remind you, tangential speed was angular speed times the radius. So we can say always their angular quantity times their radius here. But once again, if I have 2 points that are, let's say, that are moving on a circle, once again, point A and point B, okay? Do you think they will have the same tangential acceleration once they strike? The answer is no. And why is that? Because it depends on the radius. Even if they have the same angular acceleration, because their radius are different, so their tangential acceleration will be different as well. So what is tangential acceleration? Remember some keywords for both tangential speed and now tangential acceleration as well. We'll say tangential acceleration. It is the instantaneous linear acceleration which is clearly directed along the tangent of a circular path, and that is measured in meter per second squared. Remember the keywords here. For both tangential speed and tangential acceleration, the keywords are, it is the instantaneous linear speed for this, and the instantaneous linear acceleration for this one. Once again, this is measured in meter per second. This one is measured in meter per second squared. And these are what we have here. Now, where does this equation come from? Of course, you can say it comes from this one here. We said earlier that tangential, it is equal to angular times the radius here. But if we divide both sides by delta t here, what do we get? Or if it is 2 point, let's say, the object, it is moving from one point to another. Let's say it is going to speed up or slow down. So let's say speed up at this point. If we divide both sides by delta time here, of course, tangential or change in tangential divided by the delta time, that is tangential acceleration. But if it is going to change, it is rotational speed, because we said it's going to speed up at some point, or we assume that is speeding up. So change in angular speed divided by time, that is angular speed divided by the radius again. So of course you can do the same thing with the units here. This is measured in radian per second squared times meter. This radian, once you combine with other units, because it is dimensionless, it goes away. So it becomes the same as meter per second both sides, and that is the equation for tangential acceleration. So now all what you need to know is remember these two definitions and these two equations. We said tangential speed, it is the instantaneous linear speed that is directed along the tangent of a circular path measured in meter per second. And the equation for that, it is equal to omega, or angular speed, times the radius. What about the tangential acceleration? It is the instantaneous linear acceleration that is directed along the tangent of a circular path measured in meter per second squared. You can see these equations are exactly the same as what we have found, let's say, or what we had in grade 11 for tangential, by the way, or for tangential speed. That is the equation. Do you know there is another way to find tangential here? We can also, if we had the change in speed here, we can say tangential, it is equal to v final minus v initial over delta t as well. We can use this one to find tangential acceleration as well. But there is one more thing I would like you to know at this point here. Do you see, now whenever we have a linear quantity, it is equal to their angular quantity times the radius. Tangential acceleration, their angular quantity times the radius. What if I want to find the displacement? What do you think that would be? Would that also be their angular quantity, which is angular displacement, multiplied by the radius too? Yes, and that is exactly what we have. Do you remember what was the equation for, let's say, angular displacement? It was the arc length divided by the radius, yes? So now if you cross multiply here, if the object is moving in a straight line, that arc length now, it is going to be what? Angular displacement multiplied by the radius, but that will be, of course, if it is moving in a straight line, that becomes delta x, right? And that is angular displacement multiplied by the radius. Now remember this, these are the relation between linear and their angular quantity, linear angular quantity and linear angular quantity as well. Now let's go back to their definitions. And of course, there is one more thing I would like you to know at this point here. So remember, tangential speed, it is the instantaneous linear speed of an object directed along the tangent to the object's circular path measured in meter per second. Don't forget. Their equation is tangential angular times the radius. Okay, that is what we have. This is a hint, a tangent. Tangent to the circle means it is a line that touches the circle at only one and only one point here. Now remember this. It says the equation tangential, it is equal to angular times the radius, only if the angular measured in radian per second. What do we do if it is not in radian per second? Clearly, you have to convert, okay? And then you can use that in calculations. Could be, for example, what if it is rev per second, degrees per second? We can't use those, right? So we have to convert them, then we can use them in calculation. This point, I think I've mentioned this point. It says what? If the time is very short, then this arc length is so small that is nearly tangent to the circle. What do we mean exactly by this? We said that when an object is moving at a circle, here, let's say this is the angular displacement. This will be the arc length, not this one. This is going to be the arc length. Okay, this is going to be the arc length at this point here. Okay, arc length, and this is the angle theta. But that is if we can say if the time is large. What if the time is short in this case? The arc length is going to be, let's say, smaller and smaller and smaller, up to at some point here, it is going to become something like a straight line here. And this straight line, it is going to be tangent to the circle, you could say. Tangent to the circle. That is, imagine if the arc length is very small. So this arc length, you can say it is a straight line. Isn't that the same as delta x? Yes, but remember, if that is only for, let's say, if the time is very short. So the distance traveled, or the arc length divided by that time, of course, that would lead to a tangential speed. This is exactly what we mean by this point number 2. If delta t is very short, what will happen? Then arc length, you can say, is so small that is nearly tangent to the circle. Therefore, the speed, which is clearly arc length divided by the time, is then the tangential speed. That would be this point right here. Next point says all the points in a rotating object have a tangential speed, which it changes when omega and radius change. Clearly, that is also obvious. We said angular or tangential, it is equal to angular times the radius. All right, if angular changes, does not mean the tangential change because these are directly proportional. But if the radius change, clearly the tangential will change as well. Now, let me take you back to page number 20. If you remember, I said, like there were a point that we skipped. We'll say we're going to go back to this point later on. Now, I think it is the perfect time to go back to this point right here. So let's go back to page number 20. All right. All right, going back to page number 20, there were a note that we left at this point here. Do you remember this bicycle wheel? We said if we have a rigid object, once it is revolving about or around itself, let's say, we said all the points share the same angular displacement, same angular speed, and angular acceleration. But then there were this point that we left. We said point number 3, however, their translational speed differs. Why is that? That is because of different radii. Now, if we have points on a rotating object, could be a wheel, let's say, do you think they have the same, let's say now we have different circles here. Let's say this is one point, point A and point B. Do you think they will have the same tangential speed or acceleration? The answer is no. Why? Because now clearly we've just studied that tangential, it is equal to omega or angular speed times the radius. So do these points have the same radius? No. We'll say whichever has a larger radius, which is B, would have a larger tangential speed. What about the acceleration? It is going to be the same thing as well. So now we can say angular times the radius because they don't have the same radius. So the further, the bigger the radius, the bigger the tangential, the bigger the acceleration for these points that, if we have them, of course. So let's go back through this one more time. It says, however, their translational speed differ due to different or varying radii. Varying radii, that means changing the radius r, which that leads to a different linear velocity, you can say, or tangential speed, and then which also leads to different acceleration here as well. So now let's go back to this one more time. Remember now, so we said in short, all their angular variables or quantities will be consistent, and which is the same for all the points, no matter how many points you're taking. But their translational variables, whether if it is the radius, the tangential speed, or acceleration, will be different, of course, among the points because they have different radiuses, let's say. So remember this one more time. Their angular quantities will be the same, but their translational quantities will be different. And I hope you know the reason why. Let's get back to where we left, and that was this point right here. So now we've learned about tangential speed, all right? And the reason why, once again now, go back to point number 4. It says the further the point from the axis of rotation, the bigger the tangential speed. And that makes sense because tangential, we just said it, angular times the radius. So the further, that means the bigger the radius. The bigger the radius, the bigger the tangential, because these are directly proportional. So directly proportional with omega and also directly proportional with the radius. And that is what we have next. Now, the second thing that we have says their translational speed is different. Why is it different? Because they have different radius. And that makes sense, of course. For these 2 points here, the radius of R1 is smaller. So we can say V for point B, it is going to be smaller than the tangential speed for point A because the radius is larger. You can summarize all this by saying this: the angular quantities would be the same, but translationals are going to be different. Now we have this question which has also been in Wizard a few times. What does it say? It says when a wheel rotates about, let's say, an axis, when a wheel rotates about a fixed axis, do all the points on the wheel have the same tangential speed? Remember it, because we had the other question too. If it says tangential speed, do they have the same tangential speed? The answer is no. Okay, but what if they say, do they have the same angular speed? The answer would have been yes. And here's a question again. Why don't they have the same tangential speed? Because the radius of each point will be different. So again, no, they don't have the same tangential speed, but they have the same angular speed. What if I change or make this, like as a 2 question? Remember the other question we had? At this point, I'll just repeat the question. Do they have the same angular speed? The answer is yes. Okay, because all of them would rotate with the same angular speed. And of course, you can see this question been in Wizari many times here. It says, when a wheel rotates about a fixed axis, which of the following is true about point A and point B here? So I want you to look closely at the diagram because this diagram will be given if they ask this question. Point B has a smaller radius, point A has a larger radius, which clearly leads to different tangential speed, let's say. So the first question says, omega A, angular speed of point A and B will be the same. That is true, because if these two objects are rotating, they will rotate together. We said all their angular quantities will be the same angular displacement, same angular velocity, speed, and same angular acceleration. But their translational are not going to be different, not going to be the same. So this one is true, but let's keep an eye on this one. We'll just underline this one. It says angular speed for point A is larger than B. No, we said if it is a rigid object, all the points will have the same angular quantity, so it cannot be bigger. That is not true. What about this one here? It says tangential for point B, it is larger than A. Is that true? It is quite the opposite, right? Because B has a smaller radius, so cannot be bigger than A because A has a larger radius. So, but this one's saying the opposite, right? So this one is also incorrect. What if they were saying tangential for point A is larger than B? That would have been correct in this case. What about this one here? It says tangential for point A and B, all right, B and A are the same. Is that true? Do they have the same radius? No, so this is incorrect. So the only correct answer that we have is option A, don't forget. Now, what is the next point that we have? We have a sample problem, and these problems are very easy. So let's do them together. The first one says the radius of a CD in a computer is 0.0600 meter. That is the radius. If a microbe riding on the disk's rim has a tangential speed, don't forget, tangential speed, that means VT, you could say. Okay, it says the question is, what is the disk's angular speed? Remember, because the question is about tangential and angular, and we have this equation. We said that tangential, it is equal to angular times the radius, yes? Okay, but now the question says what is the angular, so you can rearrange the equation, move the r under the v, both sides divide by r, whatever you do. So angular, it is equal to tangential divided by the radius. What is the tangential that is given? It is 1.88 meter per second, and then divided by the radius, which is 0.06. The answer is going to be 31.33, and of course it continues. That is the angular, so it is going to be radian per second. That is how you can find the angular if you have the tangential speed. All right, that is clearly the relation between the two. Now we have this question too. Remember, tables, I always consider them as bonus marks, so make sure you know them because there's nothing tricky about this one. They are always very easy. We have basically tangential speed, angular speed, and then there's the radius. The first one says find the tangential. Remember, always check out for the units. If it is radian per second, you can use them. If not, you'll have to convert. So the first one is very easy. I'll leave the math for you. Just tangential, it is equal to angular times the radius. You have these two together. Just do the math for point or for part A. What about for part B? It says what is the angular? For the angular, you will rearrange the equation. Angular, it is equal to tangential speed over the radius. Once again, you have them both, all right? That is in meter per second. This is in meters, so you could do the math again without any problem. But for part C here, I'll try to do them here. What does it say? It says find the tangential, but look, the angular speed, it is given in radian per rev per second. Can I use rev per second? No, but we can always convert the rev, yes? So tangential, that is equal to angular times the radius. So I can do this right away. We said earlier that every rev, it is equal to what? It is equal to 2 pi, yeah? So that is going to be 1.2 times 2 pi, and then multiply by the radius, which is 3.8. Once you do the math, of course, you'll find the answer, and that, of course, is going to be equal to, we can say 29 meter per second, and that's it. So this is how you can find that. Of course, it is equal to 28.65, but you can round it up to 29. 9. That is for part C. This is how easy these questions can be. The last question that we have, the radius is unknown. So the radius, it is equal to tangential over angular. You have the tangential, you have the angular, no unit conversions needed, so you could just simply use them to find part D, and that'll be, the answer is going to be 1.3, all right? Give it a try. Now look at this Rosati question. This is the same as the question that we were just saying, for example, the one that you saw. Let's say this is point A, and this is point B, right? At this point, let's say point B, of course, has a larger radius, yes? Point B is smaller radius, so the tangential speed for point B is going to be larger than tangential for point A. But it could be any points, it could be any names, it doesn't matter. So let's see, what does it say? It says when a wheel rotates about a fixed axis, all the points on the wheel have what? All the points. Could be, I chose 2 points here, you could choose 10 points or 100 points, doesn't matter. Do all the points have the same angular speed and the same tangential speed? They do have the same angular speed, but is it true for tangential speed? The answer is no, because the bigger the radius, the bigger the tangential, so it is not A. Part B says they have the same angular speed, that is true, but let's check for the other. Point C says they have the same tangential, that is incorrect, because different radius leads to different tangential speed. D says different tangential speed and different angular speed and different tangential speed. No, because the angular is going to be the same, so this is going to be wrong. So now the only correct answer is option A. Make sure you know how to do that. Keep practicing. There's another question which is similar to what we have just solved. Give it a try, please. Now we have this question here, says, a small pebble breaks loose. But one more time, if the directions are not mentioned, just like we've mentioned previously, you don't have to worry about that. Just don't think about the direction at all. Just do the math, and that's it. A small pebble breaks loose from the treads of a tire with a radius of, this is the radius, but don't forget this is in centimeter. You need to convert. It says if the pebble's tangential speed, so this is tangential, Vt. What is the tire's angular speed? So we've learned that tangential, it is equal to angular times the radius. So if I want to find angular speed, it is equal to tangential over the radius. What is the tangential? It is 49 meter per second. What is the radius? Remember, this is in centimeter, right? Divide by 100 to convert to meter, that is 0.32 meter. So divide by 0.32, which the answer is going to be 153 radian per second, and that's it. Very simple, very easy. If there's questions about this, of course, you can easily grab or collect the 2 marks here without making any mistakes, inshallah. Now, at this point, we're at tangential acceleration. I've already talked about tangential acceleration, but let's just go through them one more time. We said, what is tangential acceleration? It is the instantaneous linear acceleration, which is tangent to the circular path or drawn tangent to the circular path of the object, and it is measured in meter per second squared. Because when we talk about tangential, this is the same as linear or translational. It is going to be measured in meter per second squared. If not, you could just say it is the time rate of the change of the instantaneous linear speed. Where does this come from? Now, we know that acceleration, it is equal to what? We can say it is the change in speed, or you could say velocity divided by the time, yes? But if this is the tangential here, can I say it is the time rate? We've learned that whenever we say the time rate, that is something divided by the time, yes? And then, so we can say the time rate of change of instantaneous linear speed, and that's it, which is going to be measured in meter per second squared. That's all of it. All right, what was the equation of tangential acceleration? We said it is equal to angular acceleration times the radius. And we also said, where does it come from? Which you don't need this one though, but that is the equation. Remember, if the radius for 2 points is different, then their tangential acceleration will always be different too. And regarding this note, we've mentioned before that the angular acceleration in the above equation refers to the instantaneous acceleration. The reason why instantaneous, because it could be different at every instant. This is why it is instantaneous. Okay, now For the second point here, we said for all points, or for all the points rotating about a fixed axis, their tangential speed and now their tangential acceleration will be different. Why? Because if they have different radiuses, clearly their tangential speed and acceleration will be different. Point number 3, we can say the angular speed and angular acceleration are parallel. Now that is one thing I need to mention at this point here. Okay, so think about this one here. So let's say an object is moving in a circle, we said. So we said their tangential, here's the radius, right? And then that is the point where the object is going, let's say, in a straight line. So here's the direction of tangential speed. Now, at any point, for example, if the object is going to travel faster, let's say, or even slower here, let's just say faster at this point here. So, but as in these two are in the same direction here, so we can say the tangential acceleration is also in the same direction here. So we can say the angle between the two, because these are both parallel or on the same line, we can say the angle, right? The angle between the two, between tangential acceleration and tangential speed, it is going to be 0. Why? Because they're parallel to one another. But here's another question. What if it mentions, for example, the object is slowing down? What do you think will happen? We know that in terms of in speeding up, don't forget, in speeding up, acceleration and velocity, right, or tangential acceleration, let's start with tangential. Tangential acceleration and tangential speed and tangential acceleration always have the same direction. Same direction. It is best to say tangential velocity, but we just call it tangential speed. Okay, but what about in slowing down? If it says slowing down, remember, the direction between the two, or these two, are going to be opposite to one another. So tangential and acceleration will be what? Will be opposite, or you can say it will be in opposite direction. Opposite direction. All right, what do we mean by this? Remember, now if the object is speeding up, these two will always be in the same direction no matter what. But what if the object says slowing down? Slowing down, that means it isn't another way to say the acceleration will be negative. If that is the case, what would be the angle between tangential, or let's say tangential speed and tangential acceleration? Remember, it is going to be 180 because they will be in opposite direction. One of them will be upward, the other one will be downward, and that will be 180 degree between the two. But when do we do that? Only when you clearly see in the equation that it tells you the object is slowing down. Don't forget that. Most of the questions that we have in WSAT, they never mention slowing down. They only care about or ask what is the angle between the tangential speed and tangential acceleration. We can just simply say it is 0 because these two are parallel to one another in case of speeding. But we don't care about that. Like even if you don't see speeding, the question basically itself needs that one here. Unless you see slowing down, it is always 0 degree between the two. Don't forget this one. It says this equation is valid only when the angular acceleration it is expressed in radian per second. If not, you cannot use the equation. You'll have to convert the unit, then you can use that. So here's one of the questions that we have. It says what? The angle between the direction of tangential acceleration, so here's tangential acceleration, and tangential speed. And here's tangential speed, right? Does it say slowing down? No. If it doesn't say slowing down, it is always 0. The angle between the tangential speed and tangential acceleration is always 0. Okay. We said unless if it says slowing down here, which we don't have. Now, question number 2 says what? It says for a rotating object to remain rigid, don't forget, as does a bicycle wheel, like a bicycle wheel, for example, every portion, every point on the object must have the same what? The same angular speed? Yes. The same tangential speed? No. The same tangential acceleration? Again, no. What about the same displacement? That is also a no here. So in order for something to remain rigid, all the points on the object must have the same angular quantities, whether it is angular displacement, angular speed, or even angular acceleration. All right, now moving to the next question. It says, which of the following is correct relation between tangential acceleration and the angular acceleration? Which one do you think it is true? That is option C. Well done. Okay, let's solve a question or two. What does it say? It says a spinning ride at a carnival has an angular acceleration. What does it have? Angular acceleration, which is 0.5 radian per second square. It says, the question says, how far is the rider from what, Baba? How far is the rider who has a tangential acceleration? How far from the center? Now, clearly, how far from the center? It is the radius here. How far from the center is a rider who has a tangential acceleration of this much? So are they asking for the radius? Yes. We know that tangential acceleration, it is equal to angular acceleration times the radius. So if we want to find the radius, it is equal to tangential over the angular. What is the tangential here? It is 3.3 divided by 0.5. It is going to be 6.6 meter. That is because it is the radius, and that's it. So remember, you can write a note here. Whenever the object says, or the question says, how far from the center, that is always the radius here. So whether the radius is given or unknown, how far from the center, it is always the radius, or they talk about the radius. Now we have another question. It says, a child on a merry-go-round undergoes a 1.5 meter per second squared linear acceleration. What if they did not say linear acceleration or just acceleration? How would we know whether if it is angular or tangential acceleration? You can always tell by their unit. Is meter per second squared, is it tangential or angular acceleration? Clearly it is tangential. Well done, very good. And then if the merry-go-round's angular acceleration, here's the angular acceleration, is 1, how far, again, is the child from the axis of rotation? Isn't that the same thing saying how far from the center? That is clearly the same. So we just said that angular or let's start with this. Tangential acceleration, it is equal to angular times the radius. The radius, it is equal to tangential acceleration over the angular acceleration, which is going to be 1.5 divided by 1. That is still 1.5 meter. That'll be far from the center. That's it, Yani. These questions are super easy, and they will be in Wazari, of course, sometimes. So make sure you don't lose the marks here. We have another question, which is also similar to the previous ones. What does it say? It says, what is a tire's angular acceleration? So angular acceleration, it is unknown. If the tangential acceleration at a radius of this much, don't forget, it says at a radius of this much, so this is the radius. You can tell by the unit as well, which is in meter. That is not negative. Okay, is this much. Once again, what is this unit for? That is tangential acceleration. So tangential acceleration, again, it is equal to angular times the radius. We want the angular, which is equal to tangential over the radius. Now use the two numbers here. You'll find the answer, which is going to be radian per second squared, and that's it. Easy enough. And here's the solution on the screen. All right, make sure you solve these questions here just as a practice so that you can kind of like get used to this one, and of course you know how to solve these questions for yourself. Now we have another question here which is also very interesting here. It says what? A car traveling at 30 meter per second. Don't forget this. It says a car traveling at 30 meter per second. Meter per second, that is clearly tangential. But is it initial or final? At this point, I have no idea. I'll just continue reading. It says undergoes a constant negative acceleration. Negative acceleration, remember, of magnitude of this much. So this is the negative, but look again, it doesn't says linear or angular, but if you look at the unit, it is written meter per second squared. So this is tangential, or you can say linear, but because it says negative, so it'll have to say -2. That is the second thing you need to be aware of. Now, when the brakes are applied, how many revolutions? How many revolutions is basically, they ask for delta theta, but not in radian, in revs, don't forget, okay? So how many revolutions in rev does each tire make before the tire or the car comes to a stop? Coming to a stop, that means omega final, of course, or you can say, even if it is not omega final, you can say V final, it is going to equal to 0. Is that true? Because that is what it means coming to a stop. Assuming that the car does not skid and that the tire have a radii of 0.3 meter. When we say assuming that the car does not skid, yani, imagine the tire still rotates without slipping or skidding once the brakes are applied. So how are we going to do or solve this question together? All right, let's erase this one here. Remember the numbers. The initial velocity is 3, the acceleration is -2, final is 0, the radius is 0.3 here. So this is what we have. I'll rewrite the numbers. V initial, which is 30 meter per second. And then we have V final, which was 0. And then we also have the translational or tangential acceleration, which is -2 meter per second squared. And then we also have, the question is asking for angular displacement in rev, don't forget. And then we also have the radius as well, which is 0.3 meter. Okay, so once again, remember, this question can be solved using 2 different methods here. I'll try to solve them in both methods here, but have you noticed the odd thing about this question here? So you can see that all these variables that are given here, all of them are linear, or you can say translational quantities, but the question is asking for something angular here. It asks us for angular displacement and also in revs here. So at this point, you have 2 methods here. One of them, of course, we can say, one of them here, we can convert all these to angular, let's say, to their angular quantities, and then we can find angular displacement. And then there is another method, which is we can keep it as it is. At the end, we'll convert this one to angular. I'll show you both, but before we do that, let's just convert this. Previously, we've learned that tangential speed is equal to angular times the radius, yes? So if I want angular or convert to angular, it is equal to tangential over the radius. That is what I need for the angular speed. And then for angular acceleration, it is going to be the same thing, tangential over the radius. These are the equations that I need to convert. So first, let's convert at this point here. We have, let's say, if we want to convert, let's say, tangential speed into angular, that is angular, it is equal to this point here. Angular, it is equal to 30, which is basically tangential over the radius. That is 30 divided by 0.3. In this case, it is going to equal to, that is the same as 300 over 3, which is going to be 100 radian per second here. What about for this one? Because final is 0, so if something is 0, even their omega final is also going to be 0. What about the tangential acceleration converting to angular? Let's say angular acceleration, it is equal to tangential, which is -2 divided by 0.3. That is the radius, which is going to equal to -6.67 by rounding. Let's say that is radian per second squared. Okay, now after converting these translational to angular quantities now, or linear to angular quantities, I can use or find delta theta. But there is one thing you need to be aware of, or have you noticed yet? Delta t is neither given nor required. So we're going to use which one of the 4 equations are we going to use? We're going to use the 4th equation. Why? Because it doesn't have delta t in it. So here's what's going to happen here. We'll say omega final squared, it is equal to omega initial squared plus, I'll use a bracket, 2 times angular acceleration delta theta here. This delta theta, it is unknown, we're trying to find. So once again, omega final, it is 0, 0 squared is still 0, and then omega initial, it is 100, but don't forget 100 squared plus 2 times, remember the acceleration is -6.67 times angular displacement here. Okay, so once again, that is still 0. Okay, 100 squared, that is 10,000, don't forget, plus, and then once again, I'll use the bracket because of this negative. 2 times 6.67, negative, of course, is going to be negative 13 point what? 3, almost. Okay, so 2 times negative 6.67. The answer is going to be 13.34. And then delta theta here. Look, this part is negative. Can I take this part to the other side? Yes. Will it be positive? Yes. So I'll say 13.34 delta theta, it is equal to 10,000 now. So how can I find delta theta? Divide both sides by 13.34? Yes. So I'll say delta theta, it is equal to 10,000 divided by 13.34, and of course you will find something about 750, and of course that is going to be radian, about 750 here. But I don't want radian, I want the answer in rev. So how can we convert radian to rev? Simply by dividing by 2 pi. Once you do this, you'll get delta theta in rev, which is going to be about 119 revs. That is how easily you could do this one. So that is one of the methods, of course, that we can use. What is the other method? Once again, I said there are 2 methods. You're free to choose whichever that you want to. That is entirely up to whichever you're more comfortable with. What is the second method? I'll keep using the linear quantities here, but then at the end I'll convert them. But what do I mean by this? We've learned before that we said that arc length, it is the same as the x here, which is equal to angular displacement times the radius. Do you remember this one here? So x, we said they're angular quantities times the radius, right? So, but this x now, or delta x, is the same as the arc length here. In other words, I'll just find delta x now without converting any of those. So in this case, it will be v final. Let me do that, maybe short steps here. V final squared, that is equal to v initial squared plus 2 times the translational acceleration delta x. And then I'll find delta x. Once you found delta x, which is the same, let's say, as the arc length here, that is equal to delta theta over the radius, and we want to times the radius. We want to find delta theta, which is arc length, which is the same as the delta x you just found, let's say, divide by the radius. Then you will find out that this delta x that you're going to find out, it is going to be exact, or delta theta that you're going to find out here, it is going to be exactly the same as the other one, which is 750 radian. But then again, you will have to convert this radian to rev. Then all you have to do, just 750 divide by 2 pi, then you will get something about 119 rev. So it doesn't matter which method you're going to use, that depends entirely on you. Just do the numbers here, then rearrange, simplify, then you'll find delta x, which is the same as the arc length, because arc length or delta x, it is equal to delta theta times the radius. Once you did, then you can find delta theta, that would be arc length divided by the radius, then you will get something about 750, then just divide by 2 pi so that you can get the answer in revs here. So these are both ways. You can try them, whichever the method that you prefer, and that is totally fine here. You can see that here at this point I've tried to use the second method, but the first method is always fine as well. These are some mosaic questions. I would love to see you practicing those questions and make sure you get the answer right. I think at this point we'll have to leave this one for the next session here. But once again, before we end this session, let's just summarize what we have learned today. We've learned the relation between linear quantities and their angular quantities as well. We talked about tangential speed. We said it is the instantaneous linear speed that is directed along the tangent of a circular path measured in meter per second. Remember, whenever you see the instantaneous linear speed, that is tangential speed. And then we also talked about the tangential acceleration. We said it is the instantaneous linear acceleration that is directed along the tangent of a circular path, which is measured in meter per second squared. The reason why meter per second and then meter per second squared, because these are linear quantities, just like the linear quantities you've studied them in grade 11. Okay, and we also said that for objects or for points that are rotating on a circle on a rigid object, all their angular quantities are the same, delta theta, angular speed, and angular acceleration. But now their translational quantities are not going to be different because these points are at different radii from the center. That'll be it for today. I hope you keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.